Welcome. This is a Hackerrank question called Journey to the Moon. The member states of the UN are planning to send 2 people to the moon. They want them to be from different countries. You will be given a list of pairs of astronaut IDs. Each pair is made of astronauts from the same country. Determine how many pairs of astronauts from different countries they can choose from. So in this problem, you're given 2 things. You're given a number of astronauts, n, and then you're given a list of pairs, and each pair is essentially from the same country. And what they'd like you to do is to use this information and come up with an integer that is the total number of pairs that you can make from the astronauts that you have, where each member of the pair are from different countries. So this is a fantastic question. I had a lot of fun solving this one, and if you guys want, you can take some time out and try this yourself. I have a link in the description that you can look at, and join me again when you want to compare answers. But just to give you a little bit of background about some of the technical challenges you're gonna face. So you're given n, which is the number of astronauts, and then you're given some pairs. So let's take just an example. N equals 3, and the pairs that you get could be 0, 1, 1, 2. That's 3 astronauts right there. So how many pairs can you make with this particular input? So let's say, for example, astronaut 0 and astronaut 1 are from one country. Let's say they're from America. And then astronaut 1 and astronaut 2, well, we know that they're from the same country, and we also know that 1 is from USA. So we kind of know that these guys are from USA as well. So how many pairs can you make where both astronauts are from different countries? The answer to that is 0. Because you only have one country in play here. And in fact, if you were to draw a graph of what this looks like, say this is astronaut 0, this is astronaut 1, and this is astronaut 2, that graph would kind of look like this. And this would correspond to one country. But if I were to change the question and say, hey, now you have 5 astronauts, and there's one more pair here, 3 and 4. How many pairs can you make where the output pair is from different countries? Well, now, if you look at the graph for this, so there's 5 astronauts, 1, 2, 3, 4, 5. So this will be 0, 1, and 2, and this will be 3 and 4. We know that 0, 1, and 2 are from the same country, and 3 and 4 are from the same country. So in this case, this other pair is actually, let's just pick a country here, Japan. So now you have 2 countries. So how many pairs can you make in this situation? Well, there's 1, 2, 3, 4, 5, 6. You can make 6 pairs in this situation. So you might be thinking at this point that maybe we can sort of just multiply one country times another country. But let me give you another example, and this might help define the problem a little bit more clearly. Okay. So let's say our n this time is 4, and we're just given one pair, and that pair happens to be 0 and 1. So let's work this out. How many matches do you think this would generate? Let's work it out. So there's 4 astronauts. So here's 0, 1, 2, and 3. And 0 and 1 are from the same country. So how many countries do we have in this situation? Well, we have one country here, one country here, and one country here. So how many matches can we generate from that? Well, 1, 2, 3, 4, 5. So we can generate 5 matches. But if we were to use the multiplication strategy, you'd realize that 2 times 1 times 1 is equal to 2. So it's not necessarily straightforward how to do this, and there's multiple problems that we have to solve. So now that we've talked about this question a little bit, maybe you might want to try it on your own and come back and compare answers. I guess this is the last chance I'm going to give everybody, and then we're just going to talk about solutions. Okay, countdown, 5, 4, 3, 2, 1. All right, solution time. Okie dokie. So first, I kind of probably should give you a very quick crash course on graphs one more time. So what are graphs exactly? The things that I was drawing. Well, they're a set of vertices, and it's an ordered pair of a set of vertices and a set of edges. So the balls that I was drawing are vertices. The singular is vertex, and the lines that I was drawing were edges. And we should probably be a little bit more specific than balls and edges. So this, for example, an edge is, like, you can think of it as an ordered pair of the starting vertex and the ending vertex. And that makes sense. Like, what is the defining characteristic of this line? Well, it has a starting point and an ending point. So that's how we define it. If that's the case, then how would we define a vertex? So let's just call this W. How would we define a vertex? Well, a vertex, if you look at this node here, essentially it's just two things. It's this label U, and it's the edges that the U has access to. So you could say that the vertex W is equal to the ordered pair of the label and E sub U, where E sub U is a subset of all possible edges. All right, so let's just take a look at this and see if we can find any patterns. So one thing you might notice is that vertices are defined by U, and so are edges. So this seems like redundant information, and we can probably do without this U, for this problem anyways. And so what does that do to the definition of our vertex? Well, E sub U now is, instead of being a set of U's and V's, now it's sort of just a set of V's. So V0, V1, and so on. So how would we represent this graph in code? Well, a bunch of people who are much smarter than me have come up with this idea called an adjacency list. Adjacency list. And I'm actually not liking the thickness of this brush here. Let's calm down a little bit. Okay, so what is an adjacency list? Essentially, it's a nested list. So here we have some vertices. It can go all the way up to U magnitude of V minus 1, and each vertice has a list of edges associated to it. And in our case, for this particular problem, it'll just be the ending vertex. So this might have a V1 and V3, this might have V2, this might have V4 and V5, maybe V0 as well, and so on and so on. This is not much different than what we've been talking about. So if I go into highlighter mode here, you'll see that these U's sort of correspond. Oh my goodness, that is a horrible color. Okay, let's do a yellow. Okay, so these U's correspond to this U here, and then a different color, these vertices here correspond to this and this. So we can get all the information we need from an adjacency list. And how would we represent that in code? Well, it just so happens, let's get out of highlighter mode real quick. It just so happens that we can essentially just do a nested vector. So it would be a vector of ints. So in other places, in other videos, I've done a struct for an edge, but in this case, it's really not necessary. The components of the graph are really simple. It's really what we do with it where the complication comes from. And one more thing I should probably mention before we start jumping into code is when we're talking about graphs, there's two ways we can draw it. So if I were to draw it like this with lines, this means that between U and V, this is a two-way street. So you can go from U to V and V back to U. But if I were to draw it with arrows, if I were to draw the exact same graph but with arrows, so let's draw it here. I don't know if you can see that, but if you were to draw it with arrows, here you can go from U to V, but you can't go backwards. And for this particular graph, we want to be able to go backwards and forwards. The only thing is, our edges are one way. So if we want to do an indirect graph, then we have to essentially insert two edges that are going in the opposite direction for each edge in the graph. Okay, so now I think we have enough information to start coding. So let's do exactly that. Oh boy. Ooh. Alrighty. Let's get the stylus out of the way. Okay, so what did we talk about? We said there is a V, and we said that there is a adjacency list, which is a vector of ints. And we'll just call this ADJ. And we're getting an N, and we're getting a list of astronauts. This is also a vector of ints, but it's coming in a different format than what we need. So first, let me reduce the variable name, and let's give us a little bit more room here. Okay. So first things first, let's rename the variable N to V. Then let's resize our adjacency list so we can start inserting our vertices in there. And then let's loop over our astronaut list and convert it to something we can actually use. So how do we do this? So the adjacency list, the first astronaut will be the index of the first adjacency list. So let's do I0, and that is equal to, or no, pushback ast I1. Okay, so that's the first arrow that we put in, and because this is an undirected graph, we gotta put in the other arrow, and that just means we're switching the 1 and the 0 around. And the 0 around. Okay, great. Let's now make sure everything is working, and let's just print out our adjacency list. So let's do int u equals 0, u less than v plus u, and we'll see out u and then an arrow, and then for auto v of adju, let's then print out all of the corresponding edges. So we'll print out v and then a comma, and then we'll end line. So let's see if what we have so far is working. And we'll also do a return 0 so we don't get any errors there. I don't like this comment. I'm getting rid of it. Okay. So let's run the code and see what we get. We should get some debug output. So here's the debug output, and you can see that our adjacency list is being formed here. Everything looks good. Okay. Let's comment this out. We'll keep it for debugging later. And let's keep chugging along here. Okay. So now we have to talk about components of a graph. So when we talked about the examples in the beginning, we had a graph that maybe looked something like this. And we had 5 astronauts, 2 were from one country, 3 were from another country. And the thing is, this is one big graph. Okay, this is not 2 graphs, this is 2 parts of the same graph. And what we're trying to do is we're trying to figure out how many isolated segments there are. So first of all, in graph theory, this is actually well defined. These are actually called components. So what we're thinking of as countries are actually components. I should probably use a darker color. Sorry about that, guys. And in this case, there are 2 components. So how would we figure out one from the other? So we'll use the same graph, but the algorithm that I'm thinking of is while there exists some vertex that is not visited, and that just means if a single vertex is false, I would be doing whatever comes in this loop. So I would do one thing first, but let me tell you about the second thing. The second thing is I would run DFS on a chosen node. That would be the last thing I do in this loop. And the very first thing I do is if my chosen node, whatever it happens to be, is visited, if visited U, then I would do 3 things underneath that. So first thing I do is I would have a counter that's counting the nodes in a component. So let's call it component size. So CS. This would be an integer that is started at 0. So I would So one more thing I should probably mention about DFS. While this DFS is going on, I would be incrementing this component counter, or component size is what I've called it. So inside this DFS, I'm incrementing this component size. And the first thing I would do here is I would have a vector. Essentially, I'd have a vector called capital C for components or countries, whatever helps you out. And I would append CS to that component vector. The second thing I would do is I would reset that component to 0. And the last thing I would do is I would take this U node, the one that's going into DFS, and make sure that that's unvisited. So I would set U to an unvisited vertex. And once this loop concludes, so let's do end while. Once this loop concludes, whatever is in the CS counter should be appended. And you'll find out why in just a second, because I'm going to run through this. Append CS to C. And hopefully this will get me to where I need to be to finally calculate, how many combinations can I get. It'll give me all the information I need. Let's just talk about DFS a little bit too. So with DFS, what this function looks like is that it returns nothing. So this is a void function, but it takes in a it takes in a vertex, and if this is visited, if U is visited, we return. We have no business being in this node because DFS is only an operation that's supposed to be executed on visited nodes. The second thing it would do is, if it's not visited, I would set visited to true here. And when we're running through this, you'll see why that is. And then the very last step would be for all. Let me just do this. For all V that's a neighbor of U, I would run DFS on that V. So it's a recursive function, and you guys will see you see it in action in just a second. Okie dokie. So what's the first thing that happens? Let's see if any of these are false. Well, all of them are false. U we have set to 0 right now. U we have set to 0. So has U been visited? No, it has not. So we skip down to DFS. What are we doing in DFS? I have 0, but let me just put A. Because we've lettered our nodes. So we're on node A. If node A is visited, return. So it's not visited, we can continue here. Set A to true. Okay, it's true. And one thing we're going to do inside here is we also have to update the component counter here. So we'll just do ++ CS. So we set this to true. We increment the component counter, and this might be better as a tally. So let's just forget about the 0 for a second, and we'll just do a tally. So this is 1. And then for all the neighbors of A, we DFS. So we got this one. Now we're going to B. So now we're at B. We're DFSing. Is B visited? No, it is not. We'll go ahead and set this to true and increment our component counter. Then for all the neighbors of B, we are going to DFS that. So C, have we visited C yet? No, we haven't. Let's visit it. Set visited to true, increment our component counter, and then for all the neighbors of C, we'll run DFS. Well, it turns out that there is one neighbor, there's B. So if we run DFS on B again, well, this guard clause catches it and returns out of DFS. So by now, if we run through all of these, then we're technically done. We're technically done. So this is done. Now we check again. Are there any unvisited nodes? Why, yes, there are. If that's the case, we'll append this number to our C. So now there's a 3 in here. And then we'll set CS to 0. So we're back. We're back to our starting. And then we set U to some unvisited vertex. So let's set it to D, because that's the next one in the list. And then we come down and we DFS on D. So same story. D is not visited. We set this to true. Then we increment our component counter. So now this is 1. And then for all the neighbors, we run DFS on it. We go to E, set E to true, increment the component counter. D is also an edge of E, but this guard clause catches it, so nothing happens there. And E is done. So once DFS is finished, we check, is are there any unvisited nodes? Well, no, they're not. So now we drop down to this statement here. So append CS to C. There happens to be 2 here, so let's append that. And now we're done. And the end result of all these calculations is that now we know exactly how many components there are, because the magnitude of C is equal to 2, and we also know how many nodes are in each component. So that sort of gets us to where we need to be to do the next leg of this whole thing. So let's go back and let's code this up. Okay, so what do we need? We need a visited vector. So this is a vector of booleans. Oh boy, okay, visited. And then we need to fill that with false. So for int int u equals 0, u less than v plus u. Visited u is equal to false. And we also want to resize this. So if we don't do this, then visited u doesn't make sense because that index doesn't exist. So let's just resize that to v. Alrighty. So this would be the correct setup. We also need some integer u. You know what? I'm just going to have it up here. I feel like that's going to shadow stuff. Let me just keep it local for now. Okay. So how do we then start this off? So while not all visited, so we're going to need a function to check. And let's just code that up real quick, actually. So bool, it's going to return bool all visited for I equals 0, I less than, wait, there is no global. Okay, u less than v plus u if visited u. If not visited u, then we return false. Then we return false. Otherwise, we return true. So, if all is not visited, then we do a few things. First, we check if u is visited. So, where are we going to get our u here? There is no global u. We need a local one. Well, we'll set that to be int u equals 0. This code is bothering me. Well, we know it works. It's fine. Okay, so if visited u, there are a few things that we need to do. What else do we need here? We also need an int cs, which we're going to start off at 0, and we also need a vector int c, capital C. This is going to hold all our component stuff. So what do we need to do here? So in this case, we know we're registering a component here. So first thing we're going to do is we're going to append the counter. The second thing we're going to do is we're going to reset the counter. And third is we have to set u to an unvisited node. And the way we should probably do that is for we're about to reset u anyway. So let's just use u less than v plus u. And what we're going to do here is if not visited u, we're going to break. I think that should work. We're going to break. That way u will be set to this u up here, because we're using that same U. This U up here will then be set to the index that is not visited. Okay. And then finally, if all goes according to plan, we're gonna DFS U. Okay, and one thing that I'm realizing is that this CS has to be a global. Otherwise, we're gonna have to start passing it in by reference to other places and God knows what else. Well, let's do that. And now we have to write our DFS function, which is void DFS int U. And here, if U is visited, we have no business being in here. So let's just return out. And what's the next step here? We have to increment our counter. And then for all the neighbors, so for int v of adjacency list U, we have to run DFS on it. Okay. We also have to set this visited to true here. Visited U equals true. Okay, great. So this should get us. Oh, last step, very important. We gotta push back that last CS. Otherwise, it's not gonna get the opportunity. Okay, so once we're done with all this, what we're gonna do is for auto, I don't know, C of C. Let's just C out the C with a comma, and then let's C out inlet. Okay. Okay. So this will let us know what's in that C and whether we've done things correctly. Let's run the code to see if we've done anything wrong. Hopefully we don't get any errors. Debug code 3.2. Hey, we did it. We did it. All right, y'all. I'm gonna take a quick restroom break. I'll be right back. Alrighty, I'm back. At this point, we gotta start talking about how do we calculate the actual answer to the problem. And for that, I'd like us to go back to this oddball problem where they gave us 4 vertices and only 1 pair. And just to remind you, there was 1 edge and then there's 2 hanging, and there was 3 countries total. So it was this one, and this one. And we have an algorithm that figures that out for us now. So this C, this magnitude of C is just C dot size in vectors. And the way I'd like us to approach this is to try to do it manually and then reverse engineer what we're doing manually. So let's try to find the edges manually, step by step. So the first thing we did was we took this country, this big one with the pair, and we just drew the edges. So it's and we thought maybe this is just multiplying something by something, and that's a great place to start. So we said the answer was, and we'll call this C sub 0. The answer was C times all of the remaining nodes, and the way we would get all the remaining nodes was n minus C sub 0. Okay, that's sort of me just reverse engineering what I'm doing manually. So let's continue the process. So what's the next step? The next step is to do this next calculation, which is 2. We took this other country and we can sort of draw edges to indicate where these pairs are just for this particular country. And we see that there's 3 pairs, but there's 2 pairs here that are kind of duplicates, and we don't really want to include them. So we can't just do the normal n minus C sub 1. We kind of also have to subtract these 2 nodes because they generate duplicate edges. So it's minus C1, but also minus C2. I'm sorry, not C2, but C sub 0. Oh boy. Okay, so it's also minus C sub 0. Then we move on to the next node, and how can we draw edges with this next node? Well, there's one here, but it has a duplicate. There's another one here, but that has a duplicate, and this one is also duplicated. So you know, instead of just saying oh plus 0 or something like that, let's try to be rigorous about it. And this one is going to be C2 here. So it's the same situation. We're actually trying to multiply this by the remaining nodes, but it just so happens that there's less remaining nodes. So not only are we subtracting this current node to get the remaining nodes, but we're also subtracting C1, and we're also subtracting C0, and this entire term ends up being 0. So whatever this is, this statement is going to be 0, but that's not the point. The point is, are we seeing a pattern? And I think we should be. Like, there's this here, and this term here, and this term here, and it seems to be compounding on itself. In fact, you could almost say this is kind of like a summation. Like, I could have written this statement like so. So C2 times n minus C2 plus C1 plus C0. So mathematically, these are equivalent statements. We're just distributing the negative sign up here. So something is being accrued. Something is being accumulated. And I'm going to make the argument to you that what's happening is something like this. So we're taking all of the connections, starting from I equals 0 all the way to the magnitude of C minus 1. And what's happening is we're getting Ci times n minus something. So this term. And this term happens to be let's say j equals 0 up to C minus 1. Hold on, wait, let's make sure. 0, 0, 1, 1, yeah, correct. Okay, and this happens to be the sum of all the C's that are coming this far. Okay, and this is sort of how we're getting our edges. So let's see what we did here. So this is debug. We're just making sure, crossing our T's, dotting our I's, and we are looping over. So we have our answer. Hold on. We have our answer, which is 0, and we also have this accumulator S, which will start off as 0, and then for auto, let's just call this Ci of C, just because that's what we called it during the whiteboard session. We were doing two things inside this loop, right? So first we were accumulating the answer, and that, let's just pop back and forth to make sure we're getting it right. So it's Ci times n minus S. So Ci times n minus S. And the other thing we're doing is we're accumulating this S, and let's just make sure we're getting that right. So this is, we're just adding Cj to it. In this context, Cj is Ci. In fact, this is written incorrectly. This is probably I. In fact, I think I was trying to write an I. It just ended up looking like a J. Butterfingers. Okay, so we're adding this and we're adding this. So let's just not typo or anything out. And then down here, let's get rid of this. And down here we can say, let's return our answer. All right. Okay, moment of truth. I hope I didn't mess up here. Processing. Uh-oh. So I less than ask.size plus I. N. So this n is not defined. So what is n? This is actually v. So let's rerun the code here. Okay, let me debug. I'll be right back. Hey, I'm back. So I've been questioning my life for the last 10-15 minutes, and what I have figured out is that this particular statement actually comes up here. Okay, and if I were to run this code now, it passes. And the reason is that if I were to go back here, you would see that in the very first statement, I'm not subtracting by 0, I'm subtracting by c sub 0. So the sum does have to come first. This s does have to come first. Now, if I submit this code, you'll see something interesting happen. And this is something I found just by chance. But this case 11 is going to fail. And it's going to fail for the most hilarious reason. So what Hackerrank allows its users to do is to submit test cases, custom test cases. And this particular test case is totally valid. It's within constraints. If I scroll down here, you'll see 10 to the 5th. This is absolutely a valid test, but it produces a long. So this is 4 billion. The maximum integer size is 2 billion something. And this produces a long. So it's essentially a troll. Somebody figured out how to hack it so that you would have to go into the driver code and change everything to long. I'm not going to do that, but I just thought that was funny. And I want to let you guys know. Anyways, I would be remiss if I didn't mention Cougar CS. In the spring of 2021, I was the director of tutoring for a club called Cougar CS. It's the oldest student-run computer science club at the University of Houston. This club has helped lots and lots of people get internships and entry-level jobs. As a matter of fact, I paid $30 for the membership, and I landed an internship worth $15,500. That's enough to pay for almost a year of tuition at the University of Houston. So it's definitely an amazing club, and I do encourage everybody to check it out. I have links in the description to the tutoring Discord, the main Discord, our website. I also have the paste bin of this code. So please check that out. And thank you very much for sticking around as long as you have. Thank you.